Right now, as you drift beneath the quiet weight of the night, you carry a small truth with you among the thousands of known exoplanets. Not a single confirmed system mirrors the layout of the one you call home. There is no perfect twin of a modest rocky world circling its star at just the right distance, guarded from afar by a giant companion. Tonight, you wander through the treasures of Kepler, Tess, and Gaia, moving slowly through their measurements, wondering whether your solar system is common or quietly rare within the Milky Way. So settle your breath, ease into stillness, and let this question open like a long, slow dawn. If our neighborhood is one of the strangest in the galaxy, what have all these telescopes been unable to see? And why has none uncovered a true reflection of the place you live? Across a catalogue of more than 5,000 confirmed exoplanets, not one world arrangement resembles the architecture of your own, not even loosely. That unexpected absence marks the beginning of a puzzle that has reshaped modern astronomy. It is a puzzle grounded in numbers, not imagination built from transit signals. Radial velocity curves, precise stellar wobble measurements, and sky maps that reveal how planets arrange themselves around countless stars. When NASA launched Kepler in 2009, astronomers believed they would find planetary families arranged like ours. Small rocky bodies near the star, and large giants drifting far beyond. But the universe answered with something entirely different. Something so consistent that researchers had to unlearn many assumptions about how planets grow. Instead of scattered orbits like ours, Kepler uncovered systems where planets form. Nearly matching sets, similar in size, neatly spaced, orbiting close in gentle chains. They were so orderly that scientists described them as beads sliding along a string. But the moment our solar system was placed beside these patterns, the mismatch was clear. The two shapes refused to align. Earth sits near Venus in size, yet Mars is much smaller. Distances between orbits widen abruptly. An empty band, the asteroid belt, resting where many systems host one or two large super-Earths. And farther out looms Jupiter, containing more mass than the rest of the planets combined, followed by Saturn, Uranus, and Neptune, spaced far beyond the compact formations found elsewhere. On early population graphs, the solar system didn't blend in. It drifted off to the edges, behaving like data collected from another experiment entirely. And so astronomers asked, if most planetary families follow predictable patterns, why does ours look so unconventional? One clue came from a realization that reshaped the field. Super-Earth's planets between 1 and 4 times Earth's size are the most common worlds in the galaxy, yet our system has none. This absence suggests that something unusual happened in our earliest years. In 2015, a study showed that young star systems typically build super-Earths very quickly, often within a few million years. That raised a new possibility. Perhaps our system formed them too, and later lost them. Jupiter's gravity may hold the answer. Models show that even a small inward drift of Jupiter in its youth would have disrupted emerging inner planets, scattering or crushing them before they fully formed. This idea grew into what is known as the Grand Tack hypothesis. Jupiter may have moved inward toward the region where Mars orbits now, then reversed direction and swept outward again. This single motion could explain Mars's small size, this strange mixture of icy and rocky bodies in the asteroid belt, and the absence of super-Earths today. If true, this early migration placed our solar system onto a rare evolutionary path. But data does not rely on stories alone. It also reveals what astronomers have failed to find. For years, the simplest explanation for the uniqueness of our system was that our telescopes were missing distant giants like Jupiter. Long periplanets take years to orbit. Some require decades. Since Kepler and TESS focus on short periods, distant giants remained hidden. Then came Gaia. Gaia measures a star's subtle motions with astonishing precision, tiny shifts as small as a coin seen from the moon. This method reveals planets by watching how they pull on their star, even if they never pass in front of it. When Gaia's early data arrived, researchers expected many Jupiter-like giants to finally appear. Instead, the numbers were lower than predicted, even when distant giants were discovered. Their inner systems often held compact chains of super-Earths, nothing like our mix of Mercury, Venus, Earth, and Mars. This deepened an uncomfortable pattern, rocky inner worlds paired with fallout. Giants appear to be rare. Another layer emerged from studies of stellar metal content. Stars rich in heavy elements often host many small, close-in planets. Stars poor in metals tend to host none. Our Sun sits almost precisely in the middle, an uncommon balance that may help explain why our system does not match the dominant architectures. Even the spacing of our planets is unusual. Many compact systems fall into neat rhythmic relationships, simple resonances like 2-to-1 or 3-to-2, but our planets resist these harmonies. Their orbits follow no obvious pattern, hinting that something long ago knocked them out of resonance. Taken together, these clues form a scientific picture, not a philosophical one. Our solar system does not follow the most common blueprint found in the galaxy. And this conclusion only strengthens as more worlds are discovered. Consider Kepler 90, with 8 planets like ours, but compressed far inward. Or TRAPPIST-1, where 7 Earth-sized planets fit within a space smaller than Mercury's orbit. Or HD 219,134, where multiple rocky planets cluster close to their star and none lie far out. Again and again, modern surveys reveal systems structured nothing like our own. As the catalogue grows into the thousands, the absence becomes louder. Our system consistently defies the rules most others follow. Even our Sun contributes to this uniqueness. Its rotation is slower than typical. Its magnetic activity sits in a mild range. Its ultraviolet output is steady. These traits shape the disk from which planets form, guiding temperatures, dust movement, and growth rates. Earth may orbit one of the quieter, slower, more stable stars in the galaxy. One astrophysicist once remarked, "The universe is under no obligation to make sense to you." And in the soft hours of night, that thought feels gentle rather than unsettling. What feels ordinary to you? What feels like the natural way a solar system should look may be an outlier among billions. Gaia's next release may widen the picture. Its new measurements will trace longer, subtler stellar wobbles, potentially revealing whether Jupiter-like giants commonly accompany Earth-sized worlds at similar distances to our own. If many appear, our system moves closer to average. If few do, the rarity becomes undeniable. Right now, using all we know from Kepler, TESS, radial velocity surveys, and Gaia's early data, the evidence leans toward a quiet possibility. The solar system may be the exception, not the rule. And that idea gently leads you toward a deeper question, one that expands the puzzle instead of closing it. Perhaps the conditions for life depend on more than just a planet resembling Earth. Across billions of stars, despite thousands of detected rocky worlds. Not a single system displays the full set of ingredients we rely on: a steady, sun-like star, a temperate Earth-mass planet at the right distance, and a far-off Jupiter-like guardian. This absence is one of the sharpest patterns in exoplanet research and invites a new kind of wonder. Maybe life needs more than warmth, water, and solid ground. Kepler revealed countless Earth-sized planets, some within the habitable zone. Yet even among these hopeful candidates, none sit within a planetary layout that echoes ours. And so the puzzle deepens. If Earth-sized worlds are common, why do none share our long-term stability? The first clue lies in how planetary families arrange themselves. Most rocky worlds form in tight groups, matching in size, orbiting close to their star. TRAPPIST-1, Kepler-90, Kepler-11, and others show this compact arrangement. These planets may be Earth-sized, but they do not enjoy Earth-like conditions. Their neighbors tug on them constantly. Stellar radiation washes their atmospheres with intense energy. Their surfaces flex under tidal forces. Earth experiences none of these stresses. Its orbit is isolated, gentle, and unusually steady. This stability is one of the solar system's quiet wonders. Earth shares its orbit with no twin. No giant super-Earth pulls from nearby. No close neighbor distorts its tides. Such calmness is hard to achieve without a specific arrangement around it, and that arrangement is rare. A planetary scientist captured the idea simply: if you change the architecture, you change the destiny. To feel the weight of that thought, consider the giants. Jupiter acts as a protective boundary, catching or deflecting many icy wanderers long before they reach the inner worlds. Simulations show that without Jupiter or with Jupiter closer, in the inner planets would experience far more impacts, less stable climates, and far fewer opportunities for life to persist. Yet no exoplanet system so far shows the pattern of a small inner Earth-mass planet paired with a distant Jupiter-mass guardian. This is not due to lack of searching. It is the result of 2 decades of precise measurements. Radial velocity surveys excel at finding large close-in planets. Transit missions reveal those that cross their stars. Neither method favored wide orbits. For years, researchers assumed better tools would reveal systems like ours. Then Gaia arrived sharp enough to detect stellar motions smaller than the width of a human hair seen from thousands of kilometers away. If Jupiter analogues were common, Gaia should have uncovered them. But as scientists studied the early data sets, they found fewer distant giants than expected, especially around stars with inner rocky worlds. This realization unfolds across the history of exoplanet research. In the 1990s, astronomers believed other systems resembled ours simply because ours was the only example. Then a hot Jupiter was discovered so close to its star that a year lasted only a few days. More discoveries followed, and the paradigm shifted. Kepler expanded the catalogue into thousands. Earth-sized planets proved abundant, but Earth-like conditions did not. Many worlds orbit too close, too hot, or in gravitational chains that shape their climates in unpredictable ways. TESS broadened the search, revealing the same pattern. Earth-mass planets are common. Earth-style systems are not. And one of the clearest reasons lies in planetary spacing. Across the thousands of exoplanets discovered so far, not a single confirmed solar system looks like ours. nowhere have we found a small rocky world at one astronomical unit, orbiting a quiet star, with a distant Jupiter-like guardian sitting far beyond. Tonight, we drift through Kepler's data, test detections, and Gaia's microscopic stellar wobble. Measurements to explore whether our home system is typical or an outlier in the Milky Way. Settle in, breathe slowly, and let the question unfold. If our solar system is truly rare, what have our telescopes been missing? For more than a decade, the puzzle has sharpened. Across over 5,000 confirmed exoplanets, no telescope has revealed a planetary system that mirrors the architecture of our own art. Even approximately, this mismatch isn't speculation. It comes directly from transit curves, radial velocity, plots, astrometry, and sky surveys that have mapped planetary systems with astonishing detail. When NASA launched the Kepler mission in 2009, astronomers expected to see layouts similar to ours. Small rocky planets inside, gas giants outside. Instead, they found something stunningly consistent. Worlds tend to form in families similar sizes, evenly spaced, like beads on a string. Peer-reviewed papers called it the peas in a pod pattern because the resemblance was so strong. But when researchers compared this common architecture to our solar system, the mismatch was absolute. Even the most flexible statistical models couldn't make the two structures align. Consider Kepler-11 planets, all packed closer to their star than Venus is to the Sun, all similar in size. Place Earth in that system and it becomes the odd one out. Almost every Kepler system repeats this compact family structure. Ours does not. Earth and Venus are nearly twins in size, but Mars is dramatically smaller. Orbital distances increase irregularly. The asteroid belt sits where many systems place massive super-Earths. Beyond it lies Jupiter, more massive than everything else combined, followed by Saturn, Uranus, and Neptune, all positioned far beyond the tight spacing typical elsewhere. When these differences were plotted in the early 2010s, the solar system consistently appeared at the edges of every distribution and outlier, as if it belonged to a different survey altogether. Scientists confronted a sharp question. If most systems follow predictable architecture, why doesn't ours? One clue came from the discovery that super-Earth's planets between 1 and 4 times Earth's size are the most common type in the galaxy. Yet our system has none. This absence alone is remarkable. It suggests that something prevented or removed these worlds very early in our history. In 2015, a landmark paper showed that young protoplanetary disks form super-Earths quickly, often within a few million years. So why does our inner system contain only small rocky planets? The answer may lie with Jupiter. Models show that if Jupiter migrated inward during the solar system's first few million years, even starlit would have destabilized emerging planets, scattering them or grinding them into debris. This became the foundation of the Grand Tack hypothesis, which proposes that Jupiter once drifted inward toward Mars's current orbit before reversing course and moving outward again. This single migration would explain Mars's small mass, the asteroid belt's strange mixture of icy and rocky bodies, and the absence of super-Earths. It would instantly set our system on a path few others follow. But data doesn't rely on hypotheses alone. It also reveals what has not been found. For years, astronomers argued that we weren't seeing solar system-like architectures because our tools weren't sensitive enough. Transit missions like Kepler and TESS can't easily detect long-period planets like Jupiter or Saturn. That explanation held until Gaia arrived. Gaia's astrometry measures stellar motions with microhexagon precision, sensitive enough to detect a star shifting by the width of a coin seen from the moon. When Gaia's data releases arrived, researchers expected a flood of Jupiter Nallas. Instead, the numbers were lower than predicted. Distant giants were rare, and even when they were found, their systems typically contained compact chains of super-Earths now. Think like our 4 quiet, rocky worlds. This forced a new conclusion. The combination of inner rocky planets plus distant gas giants is extremely rare. Another layer came from stellar stars with many small close-in planets tend to be metal-rich. Stars with few tend to be metal-poor. The Sun sits almost exactly in the middle, another unusual trait. Even our orbital spacing is odd. Many systems follow neat resonances like 3-2-2 or 2-1. Our planets refuse. Their periods show no simple harmony. Something must have broken those resonances long ago. Again, Jupiter is the prime suspect. Taken together, these features form a scientific case that the solar system does not follow the dominant patterns observed. Elsewhere, a case strengthened by each new dataset. TRAPPIST-1 has 7 Earth-sized planets packed within a space smaller than Mercury's orbit. Kepler-90 has 8 planets, but 7 sit closer to their star than Earth is to the Sun. HD 219,134 has multiple rocky worlds inside with none outside. These are the common systems: compact, orderly, resonant. Ours breaks the rules. Even the Sun contributes to the pattern. Its rotation is slower than typical stars of similar age. Its magnetic activity is moderate, its UV output unusually stable. Planetary formation models depend heavily on stellar behavior. Slight differences produce dramatically different planetary systems. All this suggests that Earth sits in a system shaped by one of the quieter, more stable stars in the galaxy. Gaia's upcoming Drive 4 will deepen this search, detecting even subtler stellar wobbles and long-period giants. If it finds many Jupiter-Earth combinations, the solar system becomes more typical. If not, its rarity becomes undeniable. Right now, the evidence points toward one unsettling possibility. The solar system may represent an edge case, not the average outcome. And this leads to a deeper question, one that shapes the search for life. If Earth-like planets are common but Earth-like systems are not, then habitability may depend on far more than size and temperature, even across 1 billion stars. No system yet combines a Sun-like star and Earth-mass planet at a stable temperature. Distance seemed a distant Jupiter-like protector. This absence is striking. A gap at the core of exoplanet science. Kepler found thousands of Earth-sized planets, some in their habitable zones, but none sit inside a solar system-like architecture. Most rocky worlds belong to tightly packed families with strong tidal interactions and intense radiation levels. Orbits tug at one another, surfaces distort, day-night cycles become extreme. Earth avoids all of this. It is isolated, stable, quiet. Stability is one of the rarest features in exoplanet systems. Earth shares its orbit with no equumous neighbor. No super-Earths sit nearby to yank its orbit. Jupiter blocks many comets and asteroids, reducing catastrophic impacts. Simulations show that without Jupiter, or with Jupiter placed differently, Earth's climate and orbital stability changed dramatically, and yet no exoplanet system discovered so far contains an Earth-mass planet inside with a cold Jupiter outside. Gaia confirmed the rarity. Jupiter analogues are far fewer than models, predicted especially around stars hosting inner rocky planets. By the late 2010s, the field had transformed. Earth-mass planets turned out to be common, but Earth-like conditions were not. One of the clearest reasons comes from planetary spacing. Multi-planet systems often have incredibly regular spacing and resonant periods. Kepler-223's perfect resonance chain is a famous example. TRAPPIST-1's mathematical precision is another. Our system breaks these patterns entirely. The irregular spacing implies disruptions, something that prevented the calm, predictable developments seen elsewhere. All evidence leads back to Jupiter. Jupiter formed early, reshaping the disk and starving the inner system of material. Its migrations scattered early worlds, carving a unique architectural fingerprint. The solar system's diversest tiny Mercury, small Mars, the asteroid belt, giant Jupiter, distant Saturn, far-flung Uranus and Neptune reads like a fossil record of early chaos. No telescope has found another system with the same scars. Most systems follow the Piscinopod rule, matching planetary sizes, repeating patterns, smooth growth. Ours looks fractured because something large intervened before it settled. The evidence points toward one conclusion. The solar system is the product of early, unusual, and possibly rare disruptions, not the standard path of planetary formation. And once that idea settles in, a deeper question emerges. If our system is truly the statistical exception, what story does that tell about our beginnings? Long before Earth formed and long before the sun settled into its steady glow, a profound disturbance rippled through the newborn solar system. Its source was Jupiter, not the quiet, stable giant we see today, but a freshly formed world of immense mass carving its way through the swirling protoplanetary disk. Its gravity was strong enough to reshape the early solar system, and the evidence of that ancient motion still echoes through every planet we know. When astronomers reconstructed this early era, they stumbled upon a startling possibility. Jupiter may once have drifted inward toward the infant sun, scattering young planets, sweeping aside building worlds, and leaving the inner solar system damaged, thinned, and forced to rebuild from whatever fragments survived. This idea became known as the Grand Tack hypothesis, a model not built on speculation, but on simulations, observations, and a growing list of solar system mysteries that no other explanation could resolve. To understand why scientists began to consider such a dramatic event, we must return to the earliest stage of planetary formation, when the sun was still wrapped in a swirling disk of gas and dust. Observations from Alama, the Atacama Large Millimeter Array show that young planetary disks often evolve into graceful, predictable rings, with emerging planets forming orderly chains. But the solar system does not follow this pattern. Instead, the inner planets are mismatched in size, separated by irregular distances, and entirely lack a class of planets seen abundantly around other stars. Super-Earth. This difference forced astronomers to ask deeper questions. Why is Mars so small? Why does the asteroid belt exist at all? And why is the region inside Earth's orbit so empty compared to what we observe in other systems? Early computer models tried to reconstruct the solar system as if nothing unusual had occurred. But every simulation produced the same impossible result. Super-Earths should have formed close to the Sun, yet our system has none. Meanwhile, exoplanet surveys in the 1990s and 2000s revealed that super-Earths are extremely common around Sun-like stars. If the solar system formed normally, why did it defy the galaxy's dominant pattern? That question sparked the development of the Grand TAC model. In 2012, researchers proposed that Jupiter did not remain where it formed. Instead, driven by interactions with the protoplanetary disk, it may have migrated inward until it reached roughly the orbit Mars occupies today. This type of migration is not hypothetical. We see it in many exoplanet systems: hot Jupiters, warm Neptunes, and compact resonant chains all prove that young giant planets often drift through their disks. But Jupiter's migration would have had consequences unlike anything we've detected elsewhere. A giant planet plowing inward disrupts everything in its path, clearing dust, scattering planetesimals, and preventing new worlds from growing. If Jupiter really moved this way, it would have destroyed or ejected the super-Earths that should have formed in the inner solar system. That single event explains why our system is missing entire families of planets that dominate the galaxy. It also explains the solar system's strange architecture. The inner solar system is unusually low in mass, material that should have built large rocky planets simply isn't there. In the Grand TAC model, Jupiter swept the inner disk nearly clean, leaving behind only enough debris to form Mercury, Venus, Earth, and Mars, but with far less total mass than typical systems. This same migration explains why Mars is so small. Jupiter passed close enough to starve the region where Mars was forming, depriving it of the raw materials it needed to grow. Jupiter's path also accounts for the asteroid belt's chaotic mixture of rocky inner disk objects and icy outer material, something difficult to explain without a major gravitational disturbance. But for Jupiter to end up where it is today, something had to reverse its inward motion. Simulations show how, when Saturn formed, it eventually locked into an orbital resonance with Jupiter, altering the flow of momentum through the disk. That resonance forced Jupiter to reverse course and migrate outward again, the TAC. That gives the model its name. While resonant migration is common in exoplanet systems, the precise timing required for Jupiter and Saturn makes the solar system's history unusually delicate. Slightly different conditions would have produced a hot Jupiter, a broken system, or no Earth at all. Evidence continues to accumulate. Juno's measurements reveal that Jupiter's core is diffuse and mixed, hinting at a chaotic early history shaped by collisions and gravitational turbulence. Gaia's astrometric data shows that systems with Jupiter-Saturn, analogues with similar masses and spacing, are surprisingly rare, reinforcing the idea that our system followed an uncommon evolutionary path. Meteorite studies reveal that the asteroid belt contains materials from widely separated regions of the disk, strongly supporting a scenario in which Jupiter scattered objects inward and outward during its migration. Even Earth's water may trace back to this event, carried inward by icy planetesimals, destabilized by Jupiter's motion. Taken together, Mars's small mass, the asteroid belt's diversity, the absence of super-Earths, the spacing of the outer planets, the mixture of meteorite types, and the rarity of Jupiter-Saturn analogues. The evidence forms a cohesive picture. Our solar system was shaped by a violent early upheaval. It is not a system built smoothly, but one assembled from the remnants of worlds swept aside by a roaming giant. And this leads to the next question. If giant planets like Jupiter shape the architecture of planetary systems, why are they so hard to detect around other stars? Despite their massive size and strong gravitational pull, Jupiter-like planets remained hidden for much of early exoplanet history. The problem was observational bias. Early Doppler surveys measured tiny shifts in starlight, looking for wobbles caused by orbiting planets. But these surveys ran for only a few years, far too short to detect planets with long orbits like Jupiter's 12-year cycle. As a result, astronomers found mostly short-period giants, hot Jupiters whipping around their stars in a matter of days. Their rapid wobbles were easy to detect, creating the illusion that most giant planets were extremely close to their stars. By the early 2000s, longer baseline surveys began to reveal genuine Jupiter analogues, but far fewer than predicted. Many researchers suspected this absence was not astrophysical, but observational. As one astronomer famously said, "Absence of evidence is not evidence of absence." Only when Doppler surveys extended to decades did the first long-period giant planets emerge, showing that many of them had been hiding in the slow, subtle motions that early instruments could not yet detect. You pick up the story again at the moment astronomers began to stretch their patience to almost unimaginable scales. The first true long-period giant they ever confirmed revealed itself only after nearly 15 years of quiet watching, a span longer than many scientific careers, and far longer than most missions ever hoped to operate. After that breakthrough, a few more giants emerged from the shadows, but still not in the numbers scientists expected. The next major technique, the transit method, arrived with its own hidden bias. Kepler could detect planets only when they slipped directly across the face of their star, dimming its light by a tiny, measurable amount. This method worked beautifully for worlds on tight orbits, looping around their stars again and again. But a planet like Jupiter passes in front of the Sun only once every 12 years. Kepler watched the sky for 4. In statistical terms, Kepler was almost blind to planets like Jupiter, even when a long-period world did cross its star. The alignment had to be perfect, a cosmic blink that might happen once in a human lifetime. This created a second illusion, that the galaxy was filled with close-packed super-Earths and mini-Neptunes, but nearly empty of giants drifting across cold, distant orbits. Kepler's discoveries reshaped our understanding of planet formation, but its limitations left an entire population of worlds unseen. This gap lingered well into the 2010s, shaping theories, simulations, and even expectations about how planetary systems should look. Many researchers began interpreting the absence of Jupiter-like planets as a real cosmic trend instead of a blind spot in the tools. But the deeper the models ran, the more troubling the puzzle became. Everything we knew about star-forming disks pointed toward giant planets forming commonly. ALMA images showed rings and gaps that looked exactly like the fingerprints of massive worlds. The physics of gas disks predicted that cold giants should appear frequently, not rarely, and yet the telescopes still saw almost none. The shift finally came with the arrival of ESA's Gaia mission. Gaia uses a technique called astrometry, measuring a star's position on the sky with extraordinary precision. Unlike Doppler surveys, Gaia doesn't need a planet to complete multiple orbits. Unlike transit missions, it doesn't need perfect alignment. Gaia simply watches the star move, tracing gentle shifts caused by the pull of an unseen companion. With microarcsecond accuracy, Gaia can detect motion equivalent to watching a coin slide across the surface of the Moon from Earth. That sensitivity finally opened the door to the outer giants that had escaped every previous search. Gaia's early data releases Doctor 2 and DR3 offered hints, subtle accelerations in stellar paths, quiet clues that something massive was tugging from afar. But full clarity required time, years of it, slow arcs from planets that take decades. To orbit, Gaia DR5 will contain 5 years of continuous measurements. Gaia DR5 will stretch that baseline to a full decade. Only then will the long, slow motions of thousands of stars reveal the true population of Jupiter, ANALOGUES. This approach solves the problem neither Doppler nor transit missions could overcome. Gaia doesn't need to see a full orbit. It only needs to detect the curvature, the slightest bend in a star's path. Even a faint deviation becomes a signature of a giant. For the first time, we can detect Jupiter-like worlds with orbits lasting 20 or 30 years. We can detect planets that never transit at all. We can uncover cold giants drifting far beyond the reach of Kepler or TESS. As early Gaia studies began to surface, a new awareness settled across the community. The galaxy might contain far more long-period giants than the surveys once implied. For decades, we simply did not watch long enough. One NASA scientist expressed the shift in a quiet line that stayed with many researchers. The universe rewards patience. To understand why these giants matter, you imagine the structure of a planetary system. A distant gas giant acts like an anchor. It shapes the outer debris, steadies inner orbits, redirects comets, and sculpts the pathways of young material. Without a giant planet, inner worlds face far more impacts. With one, they gain long-term stability, the same stability Earth depends on. This is why the distribution of Jupiter-like planets is more than an academic question. If these giants are common, then stable habitable zones may be widespread. If they are rare, Earth's conditions may be more unusual than we ever realized. For years, the field lacked the data to decide. Early discoveries were dominated by planets close to their stars simply because they were easiest to detect. Even missions like TESS, which scans nearly the entire sky, remain limited by their need for repeated transits. A Jupiter analog around a sun-like star just cannot transit often enough to be caught. This is where the partnership between Gaia and long-term Doppler observations becomes transformative. Doppler tracks how a star moves toward and away from us. Gaia tracks its motion across the sky. Together, they reveal a planet's full three-dimensional orbit, its true mass, its angle, its period. With this synergy, systems that once seemed impossible suddenly became visible. Gaia 4b and Gaia 5 billion giant planets orbiting unusually small stars were among the first examples. Older theories said such combinations should be rare, yet Gaia uncovered them with ease. Their existence nudged researchers to revisit their assumptions about disk, physics, and planet formation timing. But even these breakthroughs highlighted something deeper. Systems that resemble our own, with small rocky planets inside and gas. giants far outside remain extremely uncommon in current data. This rarity might reflect real cosmic scarcity, or it might simply be the final blind spot before Gaia's long baseline vision completes the picture. Gaia DR4 and DR5 will reveal which is true. If long-period giants are common, then many Earth-like worlds may have quiet protectors we never saw before. If they are rare, then the solar system becomes even more extraordinary, a system shaped by a unique sequence of timing, mass, and migration. As these clues accumulate, a quiet shift takes place, a shift born from the limits of older missions and the precision of Gaia's long watch. For the first time, the slow, graceful motions of distant stars are recorded clearly enough to reveal companions that older surveys never had a chance to catch. And once those motions come into focus, your attention naturally drifts back to the satellite that made such clarity possible. A spacecraft built not to search for planets, yet destined to unveil an entire hidden universe. You return now to the quiet motions written into the sky. Motions so faint that only a patient watcher could ever notice them. Some stars carry giants drifting tens of astronomical units away, following orbits so wide they resemble slow, cold rings wrapped around distant suns. Others reveal hints of multiple giants weaving their gravity together, shaping intricate patterns that take decades to unfold. A few stars show something even more surprising: movements so stretched across time that the planets controlling them will not complete a single orbit during Gaia's entire mission. These worlds trace only the beginning of their long arcs, yet even that fraction carries meaning. Each detection adds another brushstroke to a picture that grows more complex with every year. Planetary systems are stranger, more varied, and more unpredictable than Kepler's narrow window ever allowed us to see. Gaia's discoveries ripple outward into questions of habitability. Distant giants regulate the flow of comets and dust. Their gravity sets the rhythm of inner orbits, steadying or disturbing the paths where smaller, rocky worlds reside. By showing how many stars host these far-off giants, and how few resemble the solar system's layered design, Gaia provides the statistical ground needed to understand why Earth's long-term calm may be rare. As Gaia moves toward DR4 and DR5, anticipation rises. Thousands of new detections are expected. DR4 will bring 5 uninterrupted years of position measurements, long enough for the subtle curvature of hidden giants to finally appear. DR5 will extend that arc to nearly a decade, creating the most detailed record of stellar motion ever assembled. When these measurements join together, the galaxy's true population of giant planets will step into view. We will learn whether Jupiter-like worlds are common or uncommon. We will learn whether systems like ours follow a universal pattern or stand quietly apart. And we will see how many stars hold the deep gravitational structure needed to support stable inner worlds. As the mission continues, another realization becomes impossible to ignore. Gaia is not just counting stars, it is uncovering the skeleton of the galaxy itself, one tiny motion at a time. And once its precision becomes clear, a new curiosity rises. A gentle expectation built from the sheer volume of motion it has gathered. Each minute shift preserved in its archive hints at more structure, more long-period giants, more unusual architectures waiting beneath the data than any previous catalogue could show. With so much hidden in that reservoir of motion, the journey naturally turns toward the next step, the release poised to reveal what all those quiet years of watching have captured. Part 7. What secrets lie inside Gaia DR5's time series data? For more than 5 years, a satellite 1.5 million kilometers from Earth has been observing the stars. Not briefly, not in passing, but with a steadiness unmatched by any human-built instrument. That patience has allowed Gaia DR5 to do something no earlier mission could. It detects the long, slow signatures of giant planets that take decades to complete, even a single path around their stars. In those slow bends, traced across 5 continuous years, may rest the first true evidence of planetary systems that faintly echo our own rocky worlds inside. Giant planets far outside, a pattern that has eluded every telescope before Gaia. The scale of the achievement is almost beyond words. Gaia does not simply point at stars. It measures their positions with microsecond precision, fine enough to notice a shift as small as a coin sliding across the surface of the moon, viewed from Earth. This is the heart of astrometric tracking. Every star performs a gentle drift as it moves through the Milky Way. If a planet orbits that star, the drift bends in subtle ways, small accelerations, soft curvatures, slight deflections. These tiny deviations hide the presence of an unseen companion. For decades, astronomers detected only the fast dancers, hot giants orbiting in days or weeks. The slow giants, the Jupiter-like planets wandering in wide, cold orbits, remained beyond reach. Even advanced Doppler instruments needed decades to follow their full wobble. Transit missions like Kepler and TESS never had a chance to see planets that pass in front of their star only once every many years. Gaia changed the landscape simply by watching long enough, night after night, year after year. Its long baseline is the key. 5 to 12 years is enough for a distant giant to imprint curvature in a star's path, enough to show acceleration even without a full orbit, enough to separate a planet's pull from the star's natural motion around the galaxy. This is why DR5 is so eagerly awaited. For the first time, astronomy is approaching a genuine census of giant planets, not warped by transient chances or short mission timelines, but drawn from the actual population that exists around real stars. One researcher captured the moment with a quiet line repeated across conferences. Data is the universe revealing itself. Gaia reveals that truth through motion far too small for any earlier mission to detect. But the meaning encoded in those movements is enormous. Each tiny shift carries information about a planet's mass, its orbit, and its distance from its star. Imagine a star with a cold giant circling far away. The planet's gravity tugs gently, making the star trace a miniature orbit of its own. Gaia records this as a delicate deviation, invisible to the eye, but clear across years of measurement. With every additional year, the curve sharpens. At 5 years, it crosses the threshold where true long-period planets finally emerge. The shift is not abstract. It has already begun. DR3 revealed early candidates, faint accelerations hinting at massive companions. Among the first verified were Gaia 4b and Gaia 5b, giants orbiting unexpectedly small stars. Their existence challenged decades-old formation models, suggesting that even low-mass stars can build large gas giants under the right conditions. This is part of what makes DR4 so important. If giants can form where theory once doubted they should, what else might be hiding in the slow motions of thousands of stars? Perhaps even the systems astronomers have searched for since the 1990s. Systems with small, rocky planets inside, and gas giants far beyond, echoing the solar system's structure until now. Their absence from surveys raised quiet questions about whether our architecture was extremely rare. But Gaia's longer baseline finally frees us from relying on transits or decades-long radial velocity records. Gaia sees the sideways motion across the sky, the missing piece the other methods lacked. When combined with ground-based Doppler data, Gaia produces full three-dimensional orbits, revealing a planet's true mass and inclination. Early results have already overturned long-held assumptions. Some objects, once labeled brown dwarfs, proved to be ordinary gas giants when their true orbital tilt was measured. In other cases, signals once thought to come from a single planet turned out to be two. Even stars once believed to have empty outer regions now show subtle deviations, signs of cold giants orbiting too far out for any previous mission to detect. These corrections are not small. They reshape entire systems, adjusting our understanding built from 30 years of biased observations. As one NASA scientist remarked, Gaia tells us not what we hope to find, but what is actually there. Dr. 4 will extend that clarity. Its 5-year baseline reaches the sweet spot where planets with 10 to 20-year orbits leave unmistakable signatures. Exactly the orbit range where Jupiter analogues reside. This leads to the deeper question: how common are systems with the long-term stability needed for Earth-like worlds? A distant giant governs the flow of comets, steadies inner orbits, and shapes climates over billions of years. Without Gaia, we had no way to count how often such giants appear. Now, for the first time, the data exists. Gaia's time series also reveals subtler structures. Some stars show faint curvature, hinting at giants so distant they complete only a fraction of an orbit. Others show patterns consistent with multiple giants dividing their gravitational influence. A few reveal tiny, consistent deviations that point toward planets with orbital periods lasting many decades. Even these partial arcs matter. They identify targets for long-term Doppler monitoring. They help map where future missions should focus. They build the foundation for an unbiased exoplanet census. Researchers are especially eager to explore the region between 5 and 20 astronomical units. This zone remains almost untouched. Kepler could not see it. TESS is blind to it. Doppler service needed decades to explore it. Gaia finally bridges the gap. If distant giants are common, Earth-like stability may be widespread. If they are rare, the solar system becomes even more exceptional. This is why Dr. 4 is seen as a turning point. It fills the final gap in our map of planetary systems. It stretches our timeline beyond short orbits into the deep architecture that governs entire systems as Gaia's measurements extend across years. A new feeling begins to grow. The sense that the archive it has been building may contain far more than scattered discoveries. The motions of so many stars hint at a wave of unseen worlds ready to emerge. Worlds that could reshape how we understand planetary formation and how often structures like ours arise. And with that possibility now so close, the journey flows naturally into the next stage toward the release expected to reveal those hidden systems in full. Part 8, All Gaias. 7,500 new worlds rewrite our understanding of planetary systems. For 30 years, no mission has redrawn the map of exoplanets. In a single moment, Gaia DR5 might be the first. Astronomers once thought they understood the broad outlines. Super-Earths packed close to their stars, chains of mini-Neptunes, hot Jupiters, and a striking absence of anything resembling the solar system, but simulations. From teams across Europe, the United States, and Asia now suggest a remarkable possibility. Gaia DR5 reveal more than 7,500 new planets, most of them long-period giants, invisible to every earlier method. If this projection holds, our entire picture of planetary formation, migration, and system structure could shift overnight. This transformation begins with Gaia's method. Every star is drifting across the sky as it travels around the galaxy. Over months or a few years, that drift seems smooth. But Gaia observes for long enough, and with such precision, that it detects the faint bends caused by orbiting planets, even when they never transit, never create measurable Doppler signals, and never complete an orbit. DR4 contains 5 continuous years of this motion, covering more than 1 billion stars. At this baseline, the presence of 4 off giants becomes unmistakable. Their pull creates gentle curves in the stellar path, signs of orbits lasting 10 to 20 years or more. This population has never been accessible before. Not to Kepler, not to TESS, not to most Doppler programs. Gaia watches all of them. Across every spectral type, every brightness range, every corner of the sky. This removes the bias that has distorted our understanding for decades. One researcher summarized the shift with a line now repeated across observatories. Data is the universe revealing itself. To grasp why the projected 7,500 planets matter, consider what kinds of worlds Gaia will detect. Not hot Jupiters, those are already known. Not super-Earths. Transit missions mapped those. Gaia will reveal the slow giants. Planets like Jupiter and Saturn, wandering far from their stars. The very planets that sculpt planetary systems. These giants regulate debris, redirect asteroids, steady inner orbits, and set long-term gravitational patterns. Earth's stability over billions of years depends on this architecture. Yet, until Gaia, we had no way to measure how often such systems appear. Simulations from France, Italy, the United States, and Japan agree. When Gaia DR3's acceleration signals are extended into the full DR4 baseline, the predicted number of detectable planets falls between 6,500 and 8,000, with the central estimate around 7,500. If that prediction holds, Gaia DR4 will not just add planets, it will rewrite the map of planetary systems across the Milky Way. You begin this quiet journey by drifting outward, letting your thoughts settle as you imagine the wide circle of worlds that orbit stars far beyond your reach. In this gentle darkness, you learn that many of these unseen planets move slowly, following long paths between 3 and 20 astronomical units from their suns. They are the giants' large, distant companions whose movements are too gradual for earlier surveys to sense. Some belong to stars that never revealed even the faintest hint of a crossing shadow. Others linger around hosts that produced odd signals no one could confirm until Gaia traced the soft bending of their orbits. With Gaia's next release, the number of known giant planets will grow at once, doubling. perhaps even tripling, reshaping the foundations of how planets form. These vast worlds play a central role in the birth of systems. The way they gather material from the early disk influences everything that comes later. The mass of inner planets, the way debris settles, the movement of water across space, the spacing of orbits, and the chances that rocky planets will hold their atmospheres for billions of years. Until now, those models have leaned heavily on what we could see close to the star, mostly short-period worlds uncovered by Kepler. But planets forming far away grow under different conditions. Their presence or absence tells the hidden story of each system's early environment. Gaia's DR4 release will show that diversity clearly for the first time. You'll see stars with a single giant moving steadily, others with pairs like Jupiter and Saturn gently shaping each other's paths. A few will reveal unsettled history's worlds that drifted inward or outward before finding their place. And some will host giants so far out that they barely influence the inner planets at all. Understanding this variety requires something only Gaia can give: population-level clarity, not individual hints. Once Dr. 4 arrives, astronomers will map giant planet distributions across the Milky Way by mass, distance, orbit length, and star type. It will become the first true portrait of planetary architecture in our galaxy. One researcher summarized this shift softly: astrometry gives us the structure, not just the worlds, yet the significance reaches deeper. For the first time, we may finally ask with confidence whether any system truly resembles our own. For decades, the answer has been no. Not because such systems are absent, but because our tools were unable to find them. Earlier missions detected only the fast, the bright, the close. Gaia finds the slow, the distant, the subtle. If DR4 reveals many systems with both inner rocky planets and outer cold giants, then the solar system becomes one member of a larger family. But if such systems remain scarce, then our home may be a statistical outlier, shaped by rare combinations of timing and temperature in its earliest days. Either answer will reshape how you think about the place you live, beyond planets. DR4 carries time series, measurements that uncover faint binaries, brown dwarfs, and multi-planet systems whose gravitational pulls blend together. These details help refine our understanding of orbital mechanics, how worlds exchange momentum, how paths remain stable for eons, and how systems evolve gently over time. Early Gaia results have already revealed misidentified stars, misunderstood orbits, and hidden companions that no previous method could distinguish. Dr. 4 extends that clarity across the sky. This excitement doesn't come from speculation. It comes from the curvature already visible in stellar paths, from the accelerations detected across the catalogue, and from the realization that long-period giants are more common than anyone expected. And when the scale of Dr. 4 settles in, a new horizon quietly appears, one shaped by the years of measurements Gaia has yet to release. That horizon leads you toward the next chapter. Gaia DR5, the release expected to reveal more than 120,000 exoplanets at once. 10 full years of continuous microsecond precision measurements, motion so fine it is like watching an object drift centimeters from millions of kilometers away. A Jupiter-like world moves so slowly that traditional tools rarely capture more than fragments of its pull. A Saturn-like world takes nearly 30 years to circle its star. Neptune takes more than a century. Before Gaia, these planets were nearly invisible unless teams observed a single star for decades. Even then, their signals often remained incomplete. But Dr. 5 provides enough time for Jupiter-like giants to trace elegant curves in their stars' motions, revealing their presence with calm certainty. A decade of data also exposes slow acceleration, subtle drifts in position that betray the quiet influence of distant giants. It separates true planets from brown dwarfs and disentangles multi-planet systems that appear tangled in shorter observations. With this long baseline, the deeper structure of the Milky Way's planetary population finally unfolds. Dr. 5's power comes from combining duration with unmatched precision. No mission has ever watched so many stars for so long with this level of accuracy. This is why researchers expect more than 120,000 directly measured worlds, not statistical guesses, but planets identified by the motion of their suns. What matters most is the type of planets Gaia will reveal. Long-period giants, the cold architects of stability. These distant worlds guide debris, shape comet paths, influence the survival of atmospheres, and maintain the steady conditions that allow life to develop and endure. Before Gaia, only a few such systems were known. Most discoveries came from fast, inner planets. Kepler illuminated thousands of short-orbit worlds. TESS added more, but remains blind to the far-off giants that sculpt entire systems. Gaia fills this missing space, the outer architecture that determines whether inner planets can stay calm for billions of years. This is the region where rhythms of stability settle into place. One scientist described Gaia's mission this way: a long baseline turns motion into meaning. Dr. 5 embodies that principle. It turns millions of tiny measurements into full orbits, revealing how many stars host cold giants, how often multiple outer worlds coexist, and how these giants arrange themselves across the galaxy near the center, across the spiral arms, and throughout the halo. These patterns reshape formation models, which have long relied on small samples and assumptions. With Drive 5, astronomers finally gain population-level clarity. If the Milky Way contains countless wide-orbit giants, then the solar system may be more typical than once imagined. But if such worlds are rare, if only a few stars host Jupiter mass companions, then our home becomes a special arrangement formed under uncommon conditions. This question touches something deeper. How unusual is the place where you live? Gaia's map will show whether certain galactic regions favor the formation of Earth-like systems, whether metallicity influences the presence of giants, and whether busy star-forming clusters produce different outcomes than calm environments. Like the sun's birthplace, even the search for life depends on this. Long-term stability is essential for complexity. If Jupiter-like planets are common, stable environments may be widespread. If not, life-supporting systems may be far rarer than expected. Gaia acts as the galaxy's control sample, large enough to separate patterns from randomness, deep enough to reveal hidden gravitational structures. Even JWST benefits, using Gaia's precise orbits to study atmospheres with accuracy impossible before. Behind every Drive 5 orbit lies a quiet story. Years of observations, billions of data points, and algorithms designed to uncover movements too small for the human eye, all gathered to answer questions that have lived with us for thousands of years. As DR5 approaches, diagrams will shift, categories will expand, and boundaries between common and rare will blur. When the dust settles, the solar system will either join a quiet majority we could not previously detect, or it will stand among the rarest structures in the Milky Way. And even then, another question lingers softly at the edge of everything. What if no true solar system twin exists? Across tens of thousands of planets already discovered and many more expected, the absence of a perfect match remains. A sun-like star with an Earth-mass world at 1 astronomical unit and a Jupiter-mass giant far beyond has not yet appeared. After 30 years of searches, this pattern continues. Long-period giants often exist without inner rocky worlds. Small Earth-like planets appear without outer giants, and sun-like stars rarely show both structures together. The solar system seems to follow a path unlike most, and the reasons may lie in its earliest moments, when timing and temperature danced on a delicate edge. ALMA's images of young disks reveal that most systems form compact groups of super-Earths close to their stars. But our inner planets are irregular in size and spacing. Jupiter formed early and massive enough to disrupt that natural pattern. Saturn grew in time to reverse Jupiter's inward drift. A tiny change, a delay of a few 100,000 years, could have transformed Earth into a super-Earth or sent Jupiter spiraling inward. Gaia's long baseline will test these ideas across the galaxy. If long-period giants frequently appear alongside inner rocky planets, then solar system-like patterns may finally emerge. But if they remain mismatched, if giants rarely share space with terrestrial worlds, then our home may be an uncommon outcome, shaped by rare and fortunate conditions. Rarity is not a burden. It is a clue. It shows where nature bends toward the unusual. If the solar system stands alone after Drive 5, that uniqueness becomes part of its story, not because it defies physics, but because it followed a path that only a few systems ever take. And as you drift toward rest, you carry this quiet thought with you. Our home may be one thread in a vast cosmic tapestry, either a familiar pattern repeated across the stars, or a rare arrangement shaped by the quiet, extraordinary timing of its birthplace. Either way, the search continues gently, patiently, star by star. You drift into a quiet stretch of the night where curiosity softens and the universe feels close enough to touch. Ahead of you lies a new map of distant worlds that Gaia's next release will reveal with a clarity no mission has ever reached. For the first time, you'll be able to look across planetary systems with real, abundant numbers. More than 100,000 distant orbits. Warm, cold, inner, outer. Rocky spheres and wandering giants. Together, they form a vast tapestry that lets astronomers treat our galaxy like a living laboratory. As the patterns begin to gather, you'll see shapes in the cosmic dust, families of planets clustering in familiar arrangements, connections between size, orbit, temperature, and their parent stars. And within those emerging patterns, a quiet question floats to the surface. A question you've perhaps wondered yourself. How unusual is the place you call home? Several answers wait in the shadows. One possibility whispers that systems like ours exist, but only rarely. Gaia may uncover just a few stars with small rocky worlds inside and large cold giants far beyond. If so, our solar system wouldn't be alone. but it would belong to an uncommon group, one shaped by delicate timing during its early disk years. Another possibility suggests that systems like ours form only around very specific types of stars. Perhaps certain chemical mixtures or birth environments raise the chances of producing distant giants like Jupiter. If this pattern appears, then Earth-like systems may gather in narrow stretches of the galaxy, clustering like fireflies in particular cosmic fields. And then there is the third possibility, the one with the softest, yet most profound weight. Gaia may search through tens of thousands of planets and never find an arrangement that truly mirrors ours. No wide-orbit giants paired with a calm, inner region of small, habitable worlds. If this happens, it would mean the solar system may have grown out of a sequence of events so precise they rarely repeat. A chain that allowed Earth to hold steady for billions of years, its orbit, climate, and rhythms remaining quietly stable. Each possibility carries value. None break our models. They simply reveal how nature arranges its worlds across the Milky Way. Beneath these questions lies an even deeper scientific thread, one tied to orbital balance. In tightly packed systems full of super-Earths, planets tug and jostle constantly. Their paths shift, their tilts wander, their climates change. But giants in wide, cold orbits gyont, like Jupiter and Saturn, act as distant guardians. Their gravity softens chaos, allowing the smaller inner planets to move gently, predictably, for unimaginable stretches of time. This may be one reason Earth has remained within calm, habitable bounds. Not only because of its distance from the Sun, but because a quiet, enormous presence far out in the dark helps keep everything steady. Systems without such giants may experience far more turbulence, worlds warming, cooling, drifting off course. So, if Gaia shows that stable systems like ours are uncommon, it won't turn the solar system into an oddity. It will make it a boundary case, a rare example of what happens when early conditions align in exactly the right way. Through a full decade of careful watching, Gaia has captured something no mission has ever witnessed before: the slow, deeply woven gravitational structure of planetary systems. It sees the long curves of orbits that take decades to unfold. It senses the faint accelerations that reveal hidden giants. It measures small deviations that show planets interacting across centuries. With these pieces, astronomers can rebuild the past, how planets moved, migrated, formed, and how their long-term fates unfolded. No other mission has gathered this quiet, patient story on such a scale. And yet, even after all this, one gentle truth may remain. Even with 120,000 planets mapped, the universe might still keep its silence about an exact twin of our solar system. Not because we looked wrongly, but because the circumstances that shaped Earth's long calm may simply be rare. This thought doesn't bring sadness. It brings meaning. It tells you that understanding our origins requires looking not only at the common shapes, but also at the rare outliers, the extremes that show how far nature's possibilities can stretch. And as that realization settles, like a soft outline forming at the edge of your mind, the story of our own system becomes quiet again. A stillness grows around you. The night expands, unhurried and gentle, wrapping you in a slow cosmic breath. If you're still here, resting with me in this little corner of the universe, thank you for staying until the final moments. Your presence is a warm kindness. If this journey gave you even a small moment of peace, I'm truly grateful. A light tap on subscribe is always a gentle encouragement that helps me continue creating these night-long wanderings. And if you'd like to share where you're listening from, or what time it is in your part of the world, I would love to know. Your messages are small guiding stars along my path. Wishing you a calm, restful evening. May this night lead you toward a deep and soothing sleep.